Welcome to our last set of notes for AP Calculus. Although I can't lie, I might give you some more when you get back. We'll have to see. But this is the last official set of notes. We are still in 7.2. This would be the third day of our notes where we there together. And today's topic is volume by cross sections. We're going to start on the front page with just some review of some simple geometry. And then when we flip the page, I'll show you how this ties in with what we are going to be working on. So our goal here is to just review some geometry formulas. For example, how do you calculate the area of a square knowing that the side is A? Hopefully everyone here knows that A is A squared. Rectangles, right? You guys are all familiar with area of a rectangle as base times height, or perhaps length times width. Oftentimes, because they don't want your rectangle to have two separate variables, there'll be some sort of relation. So for example, in this example, we have a rectangle where the height is exactly half the base. That would mean that we could make an area formula specific to this particular one, and that would be A times A over 2, or A squared over 2. So that would be an area formula specific to this relationship. Likewise, isosceles right triangle, where your leg is one of the bases. That means that your two legs are equal. You all know the formula for the area of a triangle. In this specific question, if the legs are equal, then you would have 1/2 b squared. So that would be the formula for the area of an isosceles right triangle, where your leg is your base. That has to do with how we're going to be building the shapes in the next part of what we're working on. Sometimes if I give you the side length of the hypotenuse, then my work is a little bit different, right? We would need to go ahead and come up with a way of expressing that height in relation to the base. So over here, an isosceles right triangle where you're given the base, here an isosceles triangle where you're given the hypotenuse. So usually what I do here is I think about it as if I take my triangle and I think about just focusing on the 1/2 of it. That would mean that if my hypotenuse was B, then this half would be B over 2. If you recall that in an isosceles triangle, you would have symmetry. And if it's an isosceles, then this is a 45 degree, 90 triangle. So I'll put my 45-degree symbol here. And special right triangles would tell me that the height was also equal to base over 2. Or you could use tangent to come up with it. That would mean that if you are given the length of the hypotenuse, that your area would be 1/2 b times b over 2, or 1/2, I should say 1/4 b squared. If you have an equilateral triangle where you know one side length, again, if we want to find the area, we would need to calculate our height. So 1/2 base times height. In an equilateral triangle, you're dealing with a 60-degree angle, and you have that same symmetry, so this leg would be C over 2. I would like to find the height, knowing some basic trig. Oh, I fell off the side there. Sorry about that. You can now see what I wrote over here. Knowing some basic trig, tangent of 60 degrees is equal to, right, h over c over 2. Tan of 60 is √3. So c over 2 times the root of 3 is my height. That would mean that the area is 1/2 base. Well, in this case, I'm using the letter C, so let's be consistent. 1/2 times C times C over 2 roots of 3, and the area of an equilateral triangle given one of its sides would be √3 over 4 times C squared. So that would be a formula specific to equilateral triangles. Last but not least, semicircle. You guys know the formula for circle is pi r squared. So pi 1/2 pi r squared. This case, they're assuming that you're given the diameter, and diameter is just 2 times my radius, right? So if I wanted to solve for the radius, that would mean that radius equals diameter divided by 2. So that's going to give me 1/2 times pi times d over 2 squared. So specifically, if you knew the diameter of a semicircle, the area would be pi over 8 times d squared. We're going to be using these specific formulas in our work ahead. So it's a little bit hard to describe, especially since I'm not in person, but we'll do our best. We are going to sort of modify what we've been working on with the solids of revolution. So the next page starts by talking about how we created these solids of revolution by revolving our area around, and then we did our Riemann sums using cylinders. With cross sections, instead of rotating your shape and creating cylindrical pieces, you just build whatever the cross section is up and out of your screen. I can't really do it justice here just on the Elmo, but I would imagine finding the region and then building, in this case, rectangles coming out of the screen at you. So for example, it says to consider the region bounded by this parabola. We can sketch that in fairly quickly, right? If I plug in 1, I'd be right here, and it would look something like this. Y equals 0, that is your x-axis. X equals 0 is the y-axis, and x equals 1. So the region that I'm focusing on, hopefully you're starting to see them a little bit quicker now, is right here. The idea with a cross-section isn't that I start spinning this around an axis, but instead I'm going to build the same rectangles I would have built to find my area. And then from that, I'm going to take each of those cross sections and I'm going to build the specified shape. So for example, I would imagine taking that specific rectangle, picking it up and setting it down again. And from that, I'm going to build a rectangle. It says that I'm going to create the volume of the solid whose base is enclosed by this region and whose cross sections are cut by planes perpendicular to the x-axis, meaning that I am making my Riemann sum relative to the x-axis. And the heights are going to be 3. So this corresponds to each of those rectangles. But in this problem, the height is always 3 units. The trick with volume by cross sections is to come up with a formula for what that base should be. So in this problem, right, the base, the length of each of those Riemann sum rectangles would just be determined by the parabola. So that would mean that the length from the axis to that parabola was simply x squared plus 1. And I would build off of that base, I would build up and out. Imagine a set of Post-it notes, right? And they're standing up so that they're sitting right here. I'm trying to see if there's anything around me that's similar, but you know, an eraser might do the trick. I would be building this a rectangle coming out of the base at a height of 3. But it wouldn't be as thick as my eraser. They'd be really, really thin, and they would create a solid. In the end, what I'm really trying to do is just compute the area of one of those rectangles. Any one of those rectangles would be base times height, where the base is determined by the height of that parabola, and the height is given to me as 3. So my volume would be the integral, right? I would start drawing rectangles on the far left of my region at x equals 0. I would stop drawing them on the far right at x equals 1. And their area would be 3 x squared plus 1s. The width of each individual rectangle is the dx. I can type that into my calculator. You could do it by hand if you had to. This one's a pretty straightforward one, but I can compute that out. Right? I would have the integral from 0 to 1 of 3 x squared plus 1 dx. Comes out to exactly 4 cubic units. And we can change sort of the look of our build depending on what shape we are using. Here's another example. Find the volume of a solid whose base is enclosed by the given region, so same region, but this time the cross sections are going to be cut by planes perpendicular to the x-axis, and their rectangles will be heights twice that of the side in the xy plane. So the image would be exactly the same, and I would still think about picking up each of those individual rectangles traced out here in black now and setting them down again. And from that rectangular base, that rectangular strip from my Riemann sums, I'm building a rectangle. That length would still be x squared plus 1, dependent upon the quadratic, but its height is no longer a constant of 3. Its height is twice that of the side that lies in the xy plane. So 2 times x squared plus 1, right? The height is twice the base. The area of that rectangle would still be base times height, but in this example, right, the base is the x squared plus 1, and the height is the 2x squared plus 1. So I would want to find the volume by integrating from 0 to 1 of 2x squared plus 1 quantity squared dx. And that is my setup for that particular problem. If you type it in, I'm going to skip that just to save us a little bit of time. My volume comes out to be 3.733. Make sure that you are able to use your graphers like that. Rectangles are nice because they're easy to compute. Area is base times height is a really easy and familiar formula. It can get a little harder depending on what kinds of shapes you are working on. So we're going to hit the hardest one next, which is our triangles. And we'll end on a little nicer note. So let's spend some time on the triangles. Sorry for the background noise if you can hear it, just because I'm working from home. Let's see. We want to sketch out the region given by this ellipse, and you might need a quick refresher. Ellipses are usually equal to 1, so we're going to divide both sides by 36. That would be x squared over 9, y squared over 4 equal to 1. It's centered at the origin. I'm going to go out 3 in the x direction, 2 in the y directions, and I'm going to sketch in my ellipse. It asks us, right, to graph the region, so we just did that. This is the region that they're talking about. Right, we want to build off this region, and we're going to build isosceles right triangles with a known hypotenuse length of b. In other words, I'm going to take each of those slices. If I thought about computing the area, I would generate Riemann sums, right, to get the area by creating those thin slices. This time, I'm going to take each of those thin slices. Imagine I could pick up that rectangle and turn it sideways. And I'm going to let that be the hypotenuse of an isosceles right triangle. My job is to come up with a way to express the area of one of those triangles dependent upon the ellipse. And then I'll set up an integral that would add up all of those volumes so that I could have a formula. So let's go back to that front page, flip over for just a second. And we had talked about why the area for an isosceles right triangle is 1/4 b squared. You can always rewind if you need to go back and try to figure that out again. In this particular problem, though, I need to come up with a version of b that is dependent upon the ellipse, right? And that's where things get a tiny bit tricky. So I used this form to help me graph it, but I'm going to go back to this part right here. And I'm going to solve, right? This is a problem with dx because my slices are perpendicular to the x-axis. So I need this to say y equals and have everything in terms of x. So that would mean that 9y squared is 36 minus 4x squared. Divide out your 9. And y is equal to plus or minus the square root of 9 is 3. So Plus or minus is actually giving us two separate equations. It turns out, and let me see if I have enough colors here. I wish I had some highlighters. When you convert that conic section to the regular XY coordinates, the plus and the minus are going to graph as separate halves. So if y is positive, that would correspond to the top half of my ellipse. So that part that I outlined in yellow here, it would have an equation of y is equal to the positive square root of 36 minus 4x squared, all divided by 3. And the bottom half, right, would be the negative version of that. So negative square root of 36 minus 4x squared divided by 3. The area then, right, if I thought about this b, it would be to take the top and subtract the bottom. So I would have 36 minus 4x squared over 3 minus the negative square root. So minus a minus, that's plus. I get 2/3. I have 2 of them, times that square root of 36 minus 4x squared. If that is my b, then I can use that here. So my area would be 1/4. B squared, I'll square the 2/3, that's 4/9. And when I square the square root, 36 minus 4x squared. So my area for any one of these rectangles, if I knew where I was standing at in the on the x-axis, would be 1/9 times 36 minus 4x squared. That gives me the area for any one. I want to add them all together. That would give me my total volume, and that is an integral question. So my volume, right, I'm going to start over here at -3. I'm going to go all the way to +3. And I'm going to add up all those areas. So that would be 1/9. That would be 36 minus 4x squared over 9 dx. Or if you want to be sneaky, it's always easier, especially if you're doing things by hand, to plug in a 0. So you could have done, because of symmetry, 2 times the integral from 0 to 3 of the same value. I think that's the one that I typed in my calculator, just a little faster, and it works out to be a beautiful, nice integer value of 16. In the interest of time, let's try another one at the bottom. We'll skip the middle. This one says you're going to consider the solid formed where the base of the solid is the given region, right at the top. But this time, cross sections are going to be cut perpendicular to the y-axis. And this time also, I'm going to know that each of those cross sections is a side, not a hypotenuse. So that means that we are dealing with the other formula, 1/2 base squared. So this would give me the formula for an isosceles triangle's area if I knew one of the legs. Let's go back to our image at the top. I want to try to salvage the same picture, but this time I would be drawing my slices in this direction. Right? That would be perpendicular to the y-axis. So I'm going to imagine that I'm picking up each of those individual rectangles. I don't have to turn them this time because they're already lying flat. And I want to imagine that on each of those purple rectangular cross sections that I'm going to build an isosceles triangle. Right? I need to come up with a formula for my b. You can use the one that we did at the top to see why it would be equal to 2 times the square root of 36 minus 9y squared all over 4. right? So go ahead and solve your equation to say x equals in terms of y. And if you subtract the two halves, the positive version would be the right-hand side, the negative version would be the left-hand side, and you'll come up with a very similar equation as we had in the one at the top of the page. So if that's my base, right, square root of 4 is 2. So 2 over 2 would cancel, and if I have b squared, would just be 36 minus 9y squared. Let's take a break for just a second, and we'll pick up right where we left off. Hello. Oh, hi, Andy. How are you? Good, good. Is it already 4:30?